oscillations. What we're going to be talking about today is simple harmonic motion. Simple harmonic motion is systems that oscillate in repetitive motion back and forth. I put a couple examples up on the board that you may be familiar with, but we're going to start with a very simple example of a massless spring. So let's imagine that you have a massless spring and it has a spring constant K, and you pull the spring back to a distance x naught t equals 0, and you're going to let go. And I'm going to ask you, can you tell me the position of the function of time, the velocity of the function of time, and the acceleration of the function of time? Okay, well, let's start off with what we know. How do we usually approach springs? Forces are a good place to start. Let's go ahead and do that. Okay, so if I'm going to do forces, can you guys hear me okay? Okay, great. All right, if we're going to do forces, first thing you want to do is you want to draw a free body diagram of this guy. So what forces do I have? Gravity, normal force from the ground, and pulling it to the left we have kx. So I better define my positive direction as well. So I'm going to say that this is my positive x direction. Okay, so if I do my sum of the forces on this guy, my sum of the forces in the x direction, as always, is going to equal mx double dot. So let's see, the only force I have going, it looks like, is the spring in the negative x direction. Okay, so it looks like I'm going to rearrange this in a way. I'm going to bring x double dot plus, I'm going to divide everything by m. Okay, I want to make this look a little prettier. So I'm going to make a substitution that you might find a little odd. And no, it's not just because I really like drawing things as squares. Let's see if I plug that in, what I'm going to get. Okay. So if we want to try x of t equals a cosine omega t plus phi naught. Okay. What is my second derivative? What is x double dot going to be? Let's see. I take the cosine. I'm going to get the derivative of what's inside. I'm going to get negative sine. The derivative of what's inside is what? Omega. But I'm taking that derivative twice, so I'm going to get an omega squared, right? The derivative of cosine is a negative sine. Derivative of negative sine is a negative cosine, right? So I'm just going to write a cosine omega t plus phi naught. Oh, what is this? It's just x, right? So I can write this much easier as minus omega squared x. So that's what x double dot equals if this works. If we plug it in here, let me see, I'm going to get negative omega squared x for that one, plus omega squared x, and that doesn't equal 0. So it works, so that's our solution. All right. So if that is our solution, then now we can pretty easily write down what the position of the function of time and the velocity of the function of time and the acceleration are. So let's see, we already know x of t and I'm going to write these down. They're up on the slide, but I want to keep them up here for while we're working a little later. So u t, we take the derivative, we get negative omega a sine omega t plus phi naught, and acceleration as a function of time minus omega squared a cosine omega t plus phi naught. Okay, awesome. So we should talk a little constants are. So we have these constants. First we have our constant A. So what is that going to be? Yeah, so that's just our amplitude. So we also have omega. And much like, we're actually going to call this our angular frequency. Okay, from omega, we can also define that omega is equal to 2 pi over t. So t is the period of oscillation. When we put this mass on a spring, what's it going to do if we pull it back? It'll going oscillate back and forth. And it's going to repeat this motion, right? So it's going to repeat it with a period t. And we can also write that this is 2 pi times mu, where that's just a plain old frequency. And it's measured in hertz, which is just 1 over a second. Okay. So what else? We have this weird thing, phi naught. And this is just the initial phase. We're going to get some practice on this in just a second. So let me just leave that here. And then finally, the argument here, this omega t plus phi naught, that's what we're going to call the phase at time t.